Okay, up to this point, you've seen how the simulacrum system was discovered, and you've seen the unit simulacrum. And so at the end of the last part, I told you that you could make the unit simulacrum out of anything that has a unit defined. And so this is the generic unit simulacrum. It's the 4 possibilities to observe, A, and then 1. Then A over 1 or 1 over A. So the 4 pos 2 obs, and the only specification on this is that one value is 1. A can be anything. So then here's your case 1, case 2 inside Schrodinger's box here. And you've got the 4 case 1 solutions, 4 case 2 solutions. And so case 1 is A less than 1, case 2 is A greater than 1. Greater than or equal to, because the equalities mean that case 1 equals case 2 at the equality. So now let's see what we can do when we look at the unit simulacrum for other things. Are you ready to walk off this cliff with me into the unknown and challenge everything that you believe to be true, and you may never walk away from this symposium the same after you see this? This is the pi unit simulacrum. It's 2 specifications now. One value is 1. That's what makes it a unit simulacrum. And it's the pi unit simulacrum because it's the unit simulacrum with pi. So we're going to have 4 possibilities to observe, pi and 1, and then the ratio pi over 1 and 1 over pi. So now the symbol pi has a definition in our world. It's assigned the symbol 3.14159, and it is greater than 1, greater than or equal to 1 by default. So it's not going to be case 1, it's going to be case 2. So we can eliminate all of case 1 and just choose the case 2 solution that we want. And in the case 2 solutions, 2 of them have 1s that will easily cancel out. So we select those and let those 1s cancel out. And again, it comes down to 1 plus a ratio or 1 plus 1 over a ratio, as always. And so now it makes us look at the ratio. We got pi to a unit. What is the unit? Well, the unit in our system is r. The whole circle is 2 pi r, so 1 single pi is half of a unit circle. If a whole circle is 2 pi, then half a circle is pi. 2 pi is a whole circle. So just half of the circle is 1 pi. So if you're going to talk about the ratio of just pi to 1, then it was just half a circle to a unit radius. And so now this is a whole circle to r, and now it's got to be 2 pi's though, because pi was only half a circle. The whole circle is 2 pi's, still a ratio to the same unit r1, unit radius. And so the fact that you have to name this circle as 2 pi's, this guy on PBS said one time, it's like reaching your destination and saying you're twice halfway there, because each pi is a half, and so you're twice halfway there to get to the whole circle. And so that doesn't make any sense, because the pi itself, the unit definition of pi, is just half a circle. All right, so that's why the tau movement came up. There's a movement to replace the whole circle, instead of being 2 pi's, make it 1 tau. And so that's gain pop. But the problem is it's twice the value. It's 6.28. So it's a different value, and it is still based on a broken R, still living in the deconstruction. So what I did then is to look at the unit definition based on diameter instead of radius. And so now the one that's commonly, the only one that's commonly known is just pi d. It's just a unit. The definition of pi, in fact, is that it is the ratio of a circle to its circumference to its diameter. So unit diameter to a whole circle pi is the very definition of pi in that regard. So in that way, a unit diameter is a whole circle in pi here, but over here, the same pi symbol is only half a circle. So in other words, you've got the same symbol representing two things. You've got it representing half a circle in the 2 pi r construct, and you've got it representing a whole circle in the unit diameter construct. So you've got one symbol with two different meanings, which leads to the pi paradox. Because what you end up with is, go to the next slide. Two definitions. So what you end up with then is a unit circle where this unit circle is 2 pi, but the unit circle is also pi, so you have 2 pi equals pi. Because you have two different units and you're, unless you specify, so that's the pi paradox. Is the whole circle here is you're calling the whole circle 2 pi, well here you're calling the whole circle pi, and so again, you're given pi two different meanings for the one symbol. And the two different meanings lead to pi paradox. So that's how you end up with, you've got the knowledge that we have that we all learned as kids. You've got the 2 pi r circle, and then pi r squared is the area, and 4/3 pi r cubed. And you ever wonder 4/3, what, why? And if you learn integral calculus, then you learn that as you integrate and divide by the new power and twice the old, and you doubled it because of the symmetry, then you can get to that. But that's a long way to go. It's not an obvious pattern. But if you do it in the terms of the unit diameter, then the pattern becomes just super readily apparent. And so we're going to use, though, a different symbol for pi. Since the old pi represents the old system based on radius, we're going to build a new symbol for pi that contains its own meaning in its symbol, which is, here's the 3 diameters that represent the 3 dimensions of three-dimensional space that it represents, and then the circular shape, so we're talking about circular space. And so we have the symbol for pi, whole pi, and also it's that the ratio of these 2 diameters to this 1 diameter is the same as the ratio of 1 diameter to 1 r. So it's got self-similarity built into it back down to radii, because it's in the same ratio as the diameter is to a radius. So when you start building now the first, second, and third dimensions based on diameters, you get these equations then, that we get the pi d that we already know here. We get the pi d, but if instead of just you saying pi d, if instead we put it in the same form as the other equations, all of the other equations are over 2p, and so they're pi d to the p over 2p. So let's put this in that form, pi d to the p over 2p. And so what would it take to make it follow the same pattern? Well, a 2 out here in front. So the first one has an extra 2 out front to signify that it is unique and special. And then all the others are just pi d to the p. They're the exact same form, just simply increase the power. And so there's really only 2 forms of equations for all the dimensions of space. There's the first one, and then there's all the others. And you certainly would not get that from the radius dimension equations, 4/3 pi r cubed. And So once you see the pattern behind them, then you can start to ask, well, does mass follow the same pattern? And so what we'll do is we'll look at the equations for mass, starting with hydrogen and then helium, and we'll see that they actually also follow the same form of equations as the equations for space that I just showed you. So now we talked about dimensions of space and got these equations for space. It was the first dimension and then the second dimension, all other dimensions. So now we can start talking about dimensions of mass in the same way that we talk about dimensions of space, so that the first dimension of mass is in the exact same form of equation as the first dimension of space, with the extra 2 out here for only the first one to denote that it's unique and the first, and all others are just m to the p over 2p. So in all forms, I'll go back to that in a second. So in all of the equations, and these 3 equations right here are going to cover the majority of the periodic table. And it's going to be the first one, which is unique. It's got the 2 out in front, and only the first one. And then all of them have the core m to the p over 2p. That is for dimensions of mass. Follow this form. And then remember how in the very first session, video session, and then it came up again in the second, about the first decrement. The first increment in the denominator is the first decrement, or the first deconstruction. The first deconstruction. And it's right here in mass. It is m to the p over, instead of just 2p, we're going to 2p plus 1. So an increment in the denominator is a deconstruction. So we have the first dimension of mass, the second dimension of mass, and then it turns out there are 3 deconstructions, and that's actually where the dimensions of mass and space are nested together for the nested dimension model of mass. So I talked about 1 over 1, and then you just do an increment in the denominator as the first deconstruction, and so that's the same as 1 over 2. And so you do that same thing for whole pi, and this will get you to the first deconstruction of a circle is a circle with half that diameter, and then deconstruct it again and again and again. So I was just trying to show what the deconstructed nesting circles look like as we talk about mass, where we're nesting the levels together. And that was just a kind of a visual of what the nesting together looks like. So then, when we talk about the periodic table, the part that's in the denominator is just the integer mass. So for the first mass, it would be with the mass of 1, that would be 2, and then that 2 cancels out, so it's just 1 for the first mass. And then for the second mass, 2, then it doesn't go from mass 1 to mass 2, it goes from mass 1 to mass 4, and that's the way the periodic table moves from hydrogen to helium, because helium is 2 protons and 2 neutrons, so it goes from a mass of 1 to a mass of 4, and so that's what these equations do. So this is just for hydrogen, the power is 1, so put it to the power of p and 1, and it all just cancels out, and you end up with, and then for helium, it's the second mass, because it's got the second electron, but it's got an actual mass of 4. Okay, so then its integer mass is 4. All right, so you keep doing that for all of the periodic table, and what you find is that there are the first two masses are dimensions of masses. They follow the 2p over, the first one, of course, is 2m to the p over 2p. But after that, it's m to the p over 2p. Those are the first two dimensions. And then it goes to a deconstruction. It's a 2p plus 1, 2p plus 1, 2p plus 1. So then after that, then it's going to, so that takes care of, this is hydrogen, helium, lithium, beryllium, boron. And so then the next element is carbon then. So now we're back to an actual dimension of mass. So we have dimension of mass, dimension of mass, dimension of mass. Because this is m to the p over 2p, m to the p over 2p, m to the p over 2p. So it's m to the 6th, 7th, 8th. This is the mass of 12, 14, 16 for carbon, nitrogen, oxygen. And so then it goes back to deconstruction. So there's the carbon, nitrogen, oxygen. And then it goes back to a new pattern where it alternates between deconstruction, dimension, deconstruction, dimension, deconstruction. And then it goes to actual multiple deconstructions before the last dimension. And so it was alternating deconstruction, dimension, deconstruction, dimension, deconstruction, dimension. And then here's a deconstruction, and then a greater deconstruction. This is one of the few anomalies in the periodic table where the mass is greater than the one that follows. So turns out, and then finally with calcium, it's the last one that is an actual dimension and follows the dimension form m to the p over 2p. All of these up to this point, the ones in black were the dimensions of mass, m to the p over 2p. So it's hydrogen, helium, and then three deconstructions, and then carbon, nitrogen, oxygen, and then alternating deconstruction dimensions up to calcium. And that means there are 10 dimensions of mass that aligns with M theory, which is the offshoot of string theory that posits 10 dimensions plus the brain, the membrane. And so 10 dimensions of mass. So this is also known as the dimension model of mass. And it also explains the anomalies like this argon. It shows that like here's another anomaly, nickel here. So it is larger than cobalt. Is it because cobalt is anomalously large, or is it nickel that's anomalously small? Well, if you look at the equation that comes from the dimension model of mass, you can see that it's nickel that's small relative to the pattern that you see in all of the rest of the row. It is anomalously low. So that explained, the dimension model of mass explains that nickel is the low anomaly there and not cobalt being high. Whereas for argon, it was definitely high. It's the anomaly high because it stands out of the pattern from the other row that it's in. So the dimension model of mass explains and allows you to see which elements are actually the anomalies and which are not. So argon was the anomaly, it was anomalously high. This was anomalously low. This one's anomalously high, it's plus 12. And then this is an anomaly that was plus 26 versus plus 19. So the dimension model of mass allows you to see by putting it in that form of equation, and then this is the deconstruction level, then just looking at the values for the deconstruction, you can see which are the regular deconstructions, which are the anomalies, and which are the true dimensions, the 10 true dimensions. So the first dimension of mass was m to the p over 2p, but just with that extra 2 out there to designate the first. Now I did look at a couple of possibilities to better. What we've been talking about up to now was the integer mass, integer mass of 4, integer mass of 12. Well, the masses are more specific in reality. They have what's called the mass defect, and they're a little bit away from the integer value. And so I looked at a model, and for the first mass, hydrogen, this model is 99.989% accurate. So it's called the dimension, it's called the 99.989% solution, original name. And so it is actually that pi over 3 to the 1/6 equals 99.989% accurate to the accurate model of hydrogen that's observed, not the integer mass. So this value gives 1.00, the calculated 99.9% solution, and the value is 1.07825, and that's actually changed a little since I made the slide. The National Institute for Standards and Technologies changes the mass of our reality, and it is actually a little different for that. So that I just wanted to show that although I've presented the dimension model for the integer, I also do have, you know, the 99.989% solution that envisions, you know, tying them all together through circular dimensions of space and mass. And so that's how mass spectrometry of fats and oils led me to the simulacrum, and then to the pi paradox, and then to whole pi, and then to a new understanding of dimensions of space, and then dimensions of mass, and then you've got the whole ball game. Okay, thank you very much. See you on the YouTubes.